Hi, I'm glad to introduce my Tbooster, adaptive touch boosting for mobile texting. My name is Kwangmin Lee, and I'm from Yonsei University in Korea. When we use smartphones, all our interactions works with touch event. And when we use surf internet or type texts or taking pictures with touch events. And this is very frequent, and so its responsiveness is very important for users' quality of experience. But current default Android governor cannot guarantee this responsiveness, and for users' quality of experience, this immediate boosting is required, and that is touch boosting. So, existing touch boosting in smartphones simply fix the minimum CPU frequency to a specific one. Basically, when users touch the screen, it locks the minimum CPU frequency to a specific one, and when users take off the finger from the screen, it unlocks the frequency. Although there are some second steps and some tail times, it is all fixed values. So it is straightforward, but is it good enough? Among various touch events, we focused on mobile texting because, as you can see from the graph, mobile texting is the most frequent mobile activities. For mobile texting, there exists diverse text input user interfaces, like writing receiver's email address, searching emails, or finding friends in social network service, or post some writings and type some URLs and type some search keywords. So those diverse text input user interfaces often have many functions to provide better user quality of experience. So those things makes various texting workloads. Autocomplete functions also is the one that makes diverse workloads, as you can see below. But current existing touch boosting is too naive to compare with these diverse texting workloads. So we think that it could be the waste of energy. And we conducted preliminary experiment to what's really going on in real world. So first, we conducted some user survey to identify the frequent texting applications using soft keyboard and to measure the real users' texting intervals. So as a result, we could pick 10 target applications in 5 application categories, like instant messaging, social networking service, memo applications, browser applications, and email applications. We also can get 6 texting intervals for further experiments from this texting interval user data: 75, 100, 150, 200, 300, and 400 milliseconds. Next, we measured the power consumption due to touch boosting in previous applications. We used Galaxy S5 with Android KitKat, and we also used Android Monkey to maintain the fixed texting interval during the experiment. For each 10 applications, we tested 2 different input UIs and power consumption measured with Monsoon Power Monitor. Results shows that power consumption is very different by applications and type of texting UIs. And when we apply the touch boosting, their power consumption increases about 13%. We further analyzed the result by CPU frequency usage. This is the results without touch boosting. And if we turn on the touch boost, we can see that large increases in higher CPU frequency usage ratio. And this is the fixed high frequency usage by current touch boosting. Moreover, we define the texting latency as time delay before input text is displayed on the screen. And we measure the texting latency with various texting intervals. This result shows the touch boosting. And when we turn off the touch boosting, and when we turn off the touch boosting, texting delay sure increases. But in many cases, their differences is not significant. So if we just disable the touch boosting and can have more power savings in those cases. So it is clear that current touch boosting technique can be optimized. So we designed the Tbooster, adaptive touch boosting for mobile texting. Tbooster, from touch event, Tbooster first measures timings, such as texting latencies or texting intervals. From that timings, Tbooster determines response time thresholds. Based on thresholds, Tbooster determines proper boost level. Finally, Tbooster can achieve adaptive touch boosting by various boost levels. So there is one challenge to implement our Tbooster. That is, determine thresholds that do not reduce users' quality of experience. So we had to figure out how quick is enough for users or how sensitive are users. So we call it as critical texting latency. To determine the critical texting latency, we first conducted user study. This user study done with applications have many buttons with different latencies. And graph shows that if texting latency overs 100 milliseconds, users' rating suddenly drops. So we assume that users cannot distinguish texting latency below 100 milliseconds. So we set it as a critical texting latency. But what if texting input interval is lower than 100 milliseconds? In the previous user study, there certainly exists some amount of percentages below 100 milliseconds of texting interval user data. So we conducted another experiment. We set a texting interval as 75 milliseconds and varied touch boost level to get different texting latencies. In this case, all texting latencies are not exceeding texting intervals and shows moderate increasings. But in other cases, like more workloads, texting latency skyrocketed. This is because the nested operations described in this slide, each workload starts before previous one is complete. So this nested operation causing the additional latency, and this leads to this sudden increase. So we have to prevent this situation. Finally, we could build some simple algorithm for critical texting latency. So if texting interval is smaller than latency, we set the interval as threshold to prevent such previous situation, to prevent sudden increase of texting latency. And if texting interval is larger than latency, we set 100 milliseconds as threshold to guarantee the quality of experience for users. As a result, Tbooster shows increasings in texting latency. But this does not reduce the user's quality of experience because it is all within the threshold that guarantee the quality of experience we surveyed. And that reduction leads to power saving. And in aspects of CPU frequency usage, Current touch boosting seems a little skewed to higher frequency. But with our Tbooster, higher frequency usage decreases and lower frequency usage increases. And this shows the our adaptive boosting technique works well. And among various texting intervals and various applications and texting input UIs, Tbooster shows average power 8.95% of average power saving. And Tbooster shows approximately 0.97%, 93% of additional power usage. And in real usage scenario of applications, Tbooster shows 6% of average power savings. So we further discussed about the scalability of Tbooster. Basically, Tbooster is applicable if the device's original touch boosting code is accessible. So devices with Snapdragon application processor, which uses MP Decision daemon, might have some issues with Tbooster because MP Decision controls the touch boosting, and we cannot access that code. Finally, we confirm that Tbooster is applicable to many devices like Galaxy S4, 5, 6, and Note 4, 5, and Nexus 5X and 6P. Conclusion, we saw the necessity of new touch boosting for soft keyboard texting. Current knife touch boosting could be optimized when texting with soft keyboard. No considerations for diverse workloads with various applications leads to waste of energy. So we have proposed an adaptive touch boosting system for texting. It dynamically adjusts touch boost level on the basis of texting latencies and texting interval. So Tbooster reduces device's power consumption by 4.6 to 13.1%. Thank you for listening.
Hi, Gregory from Georgia Tech. If I understand your contribution here, it's when you have a soft keyboard,
yeah.
you're gonna change the kind of sampling rate in order to give the right kind of feedback to a user using that keyboard. And you say it's different for different applications. Great, but wouldn't that apply to any soft interactive widget you'd have on your display? So why just limit your analysis to just the keyboard?
That is because the main challenges are the texting latency, that how quick is enough for users, and how sensitive for users. So you have to find the endpoint of interaction.
Sure, no, I understand that. But for example, if I've got any button on a display and I want to give someone feedback that they touched that particular button, you'll need to sample to. So it could apply to anything in addition to the keyboard. I'm just saying you got a more general profile here.
So I'm currently expanding this work to what you said.
Yeah, okay. The last thing is a minor point. The title for your paper suggested to me that this was literally about text messaging. When you say mobile, I think you mean mobile text input or just mobile typing. Would have been clearer. It's just an English language issue. I wish we could change the title in the ASIM library because it'll be more clear to the reader. But thanks.
Hi, I'm Minong from Rice University. I'm confused with the term the texting latency. So can you clarify what is the duration for the texting latency?
Find the texting latency from the user